yeah, so we'll maybe just wait for one or two more and then I'll jump in. I'm going to switch over to the previous lecture set and then come back to this one just so we can pick up a few slides that we didn't get through last time. And we'll see, I think we can get through everything today. We really only have about 4 exercises to do. So it'll be mostly me talking and a little bit of you guys doing some coding, hopefully. Let's see how we do on time. Oh, and by the way, we're going to record this time. A couple people asked to give that a try, so I'll record it and I'll see if I can edit off the stuff on the front and the end. But just to let everybody know, it'll be recorded. I'll put that in the messages too, just so everybody knows. Record and got the link after. Okay, so. Okay, so let's get started. I'm going to switch over to lecture 20, just pick up a few slides from the last one. Let me try to do that this way. So I'm going to go to, where did the other PowerPoint go? PowerPoint 2120. All right, sorry. I'm going to have to turn off the presentation on PowerPoint in order to do that switch. Okay, so PowerPoint. Sorry guys, I thought I had this all set to go. Let me just make sure that I have my PowerPoint lecture 20 ready. New share. There it is. Okay, there we go. Got it. Okay. All right. Do you guys see the deep versus shallow copy? Anybody? Just give me a thumbs up if you see it on your screen, hopefully. Yep, good. Okay, great. Thanks. All right, so let's get going. All right, so basically, this is going to be a theme that I'll keep coming back to just to help everybody get more comfortable with what we're going to be building in the next homework. So the idea of deep versus shallow copy revolves around how well we do when we make a copy of an instance, and especially if that instance ends up having a lot of memory hanging off of it. So we're going to look at a couple examples, but essentially the copy constructor and the destructor and the assignment operator that we talked about last week, those things work together to give us this behavior that allows us to kind of wrap a class inside of this behavior and really make it do useful things. And often this is referred to as the rule of 3 idioms. So idioms are kind of like patterns in programming. They're kind of a collected way of thinking about a particular problem. People tend to solve them in a similar way. So if you ever search for rule of 3, you'll kind of get this, especially relating to C++. It basically means, hey, if you're going to implement a class to sort of manage a bunch of services, you're very likely going to need a copy constructor, an assignment operator, and at least a destructor. And you might need a few other things as well. So we're going to end up playing around with that a little bit today. So, and as we mentioned, C++ gives you this default copy and assignment behaviors, but they're not very good. They're super shallow. So here's a couple pictures that will hopefully illustrate that idea. Just clear off my desk a little bit here. So let's say we have a puzzle, which is what we're going to be doing in our next homework assignment. Essentially, we have this puzzle, like a jigsaw puzzle, and it's got this this pointer to some pieces. That's a dynamic array of pieces, and then just a grid, which is very similar to this 2D vector grid we've been working with all along here. So if I were to create a dynamic array of pointers and then point those pieces to that dynamic array of pointers, and then go ahead and create the instances of each puzzle piece, we'll call that a token, but each of those tokens is really a piece of the puzzle, right? Imagine it has a little picture and some sort of edges on it that fit together. So if we did something like that and we create a second puzzle, puzzle P2 equals puzzle P1 with a system copy, what's going to happen is we're just going to create a second instance of puzzle P2 there, and it's going to just copy the pointer value over from pieces. So the pointer value on P1 is going to get copied to P2, and now these two instances look like they're separate, but they're really sharing a pointer to the same dynamic array, right? So that's what we would call a shallow copy, right? So that copy, you know, could be okay if it's okay to have all this dynamic memory here in orange shared by the two puzzles. But very often when you make a copy of something, you think you've made a complete copy. And so this is not a complete copy. This is a shallow copy. So let's take a look at kind of the next level up on that, right? So I should point out, oops, oh yeah, I put a few audio things on there to help you if you come back to this PowerPoint. So here's example 2. So puzzle 1, again, we've got the same kind of situation, right? And then if we actually, instead of using this just a system level copy operator, if we did something a little bit more involved where, let's say, we created a duplicate of this array of pointers, but they were still pointing to the same tokens in the middle, we've sort of improved our copy a little bit. It's less shallow, right? But we still have this overlap in the middle. There's still two puzzles kind of pointing to the same tokens in the middle. You know, let's say we failed to copy those when we implemented our copy constructor. We accidentally just borrowed the pointers from each of the dynamic arrays. And so if, let's say, somebody came and deleted one of those puzzle pieces from one puzzle, it would leave us with a corrupted pointer in the other puzzle, right? So we could crash, right? So we have to be careful in these situations that if we are expecting these things to be true copies, they may not be. Now, the best thing we can do, second example, whoops, the best thing we can do, of course, is just go ahead and do the full copy. So if our copy constructor really does a great job, it's going to walk through the entire data structure off of puzzle P1, make copies of everything that are completely unique, no shared pointers whatsoever, and now we have a true copy. So one puzzle can get deleted, or any puzzle pieces can get changed or rearranged and not affect the other puzzle. Very, very often when you're copying complex data structures like this, bugs arise much further down the path because you've copied it, you feel good about copying it, you think you did a good job, but somebody deletes one of the original things, and then suddenly you have a segmentation fault in your copy when you try to traverse that data structure. So it's really important to get your copy constructors right, and as we'll see with the assignment operator, it's similar there too as well. So that's our deep copy. So the moral of the story is we just have to design our stuff very carefully and make sure we do a very thorough job. And that's what we're going to do in our lecture today. So jumping forward to, we'll jump forward to lecture 21. Does anybody have any questions just kind of on that concept right there? Just jump in if you do, or go ahead and chat if you like.
Couldn't find what slide that was.
Oh, so we're on lecture 20, and that was probably probably 8 slides from the end of the lecture set. So it's way at the end, yeah.
All right.
So I was just sort of picking up some stuff that we missed at the end of the lecture last time. So.
All right, gotcha.
Okay, so give me just a moment. I will go ahead and switch us over to today's lecture set. So let me try a new share. And then we're going to go, now we're going to be on lecture 21. So this is our kind of our last big set on dynamic memory, or at least under that title. So, so let's see, now I'm going to go over to this guy here. All right, good. So that's 21. And then we'll start from here. Whoops, not great. Too many windows. All right, let's try that one more time. Slideshow, play from start. Okay, does everybody see lecture 21, dynamic memory management? So give me a show of hands if anybody sees that, just so I know. All good? Great. All right, thank you. Appreciate that. Okay, so let me stretch some things out here a little bit just so I can see what's going on in my windows. Okay, yep, I guess we're all here. Sorry, I'm just trying to make sure I got things arranged. Okay, so let's talk a little bit about stuff, just quick review, schedule, and then we'll do a very quick review on the stuff from last lecture, but we won't go too deep. So we're on week 12 here. So I'm gradually watching our progress. I might move the thread topic out, but otherwise we're going to be introducing homework 7, which is our jigsaw puzzle. Of course, everybody finished or was in the process of finishing the Boggle homework and quiz 4. And so we're going to move on to 7, which will be a dynamic memory project. And then not until next Monday, I'll release the quiz 5. So we'll have 1 week to do that. And all the rest is pretty much the same that we've seen so far. Just a reminder, if you want to give any feedback anonymously, feel free to do that. Apologies, there were just a couple people that gave me some feedback and I didn't realize the things weren't set, but it's all on anonymous now. So you don't have to worry about anything negative affecting you. If you want to say something constructive or critical, it's fine with me. And then I did want to just mention for quiz 5, there was a pretty tricky question set, and I just wanted to go over this because I had something wrong, and it's also a very complex subject. We won't really have too much on this on the final exam, but I just wanted to go through this in case anybody had any questions. So and this is a very subtle thing too. Like when we get a color and we return a string, a literal string, we're getting an address of this red string that's in the special area memory that's read-only. So there's nothing wrong with returning that particular pointer right there. This one is problematic, this example here, because what we've done is we've created a local variable here, or a local array of characters. We've initialized it locally with the letters RED. And then we return the pointer to that, or we return the array, that is, which is essentially a pointer to a character. And that's going to cause the compiler to complain, because what we're really doing is returning a pointer to some local memory that's just local to that function, right? And so that's a no-no, really. That's something that's guaranteed to blow up if we access that pointer. Now, this one I had configured poorly. So this really was a bad example, right? And so one of the questions had two bad examples on it. And so that introduced some confusion, and I'll be correcting anybody who got that question to make sure it's fixed. But I fixed it this way, right? So if you take those 2 examples and you just kind of convert this into a static pointer, right? What we're doing is we're storing that for the duration of the program and initializing it with the pointer to this special area memory, and then we're returning that static pointer. That's okay. It's a little bit bad form to do that, but it works. The compiler's not going to complain. So that's really the fix for that question set, if any of you were confused on that. And then there were a few other examples of things you could get away with that were actually okay to do. So I just kind of put them all here so you can take a look at those. Let's hold on a sec. Somebody had a question. So when you return a literal, a literal meaning like this word red. So if you've stored the address of RED in a static, or even just here, like char star get color 1 return red, you're just returning the address of something that's been allocated at compile time, and it's in a special area of memory that's read only. So it's safe. It's safe to return that pointer. It's kind of like a static variable that's available at file scope. I believe it's available at file scope. And you can read it, but you just can't write it. It's a read-only area of memory. So that's all we're really doing in this case, right? We're returning a pointer to that read-only chunk of memory. Similarly here, when we assign that pointer to static const char, we're basically initializing the address of ARR, or we're returning the address of ARR with the address of red. It's not great form, but you can definitely do that. So yeah, not temporary. Yeah, those things persist. If it's something like that, it's going to stick around in that read-only memory because it's created at compile time. So let's see. So another thing, I think it's a little time has passed on this one for most of you, but I just wanted to point out there is a tricky thing that actually was relevant to our lecture on Thursday. So I thought I'd bring it into the conversation here. When we talk about automatic conversion, which we talked about briefly on Thursday of last week, what we were saying is when you have a constructor that can get away with being given only one argument, C++ is automatically going to try to convert that argument. So if I did something like this, token t equals A is clearly not a token, right? So assigning A to a t wouldn't generally make sense, but it turns out that with these default row and column settings, we can actually expect C++ to create a token instance out of that automatically through automatic conversion to create a token instance out of a character. So it'll use basically the main constructor to do that. But the problem for some folks, and it's an understandable one, it's very tricky, is that when you print that out, what you find out is you've just created a token at 0, 0 because our row and column defaults are at 0, 0. So it's okay if you want to create one that way, but you need to understand that you just sort of created a token at the origin or at 0, 0 or the upper left corner of the grid. So which may or may not be what you were thinking of. But that's a good example of where if I had put the word explicit in the .h file, then it probably would have saved some people some trouble because it would have come up with a compiler bug at compile time. It would not have allowed you to do that conversion. It would have said, hey, can't do that. That actual constructor is explicit, which means I'm not allowed to do my little magic conversion thing. So, so that probably would have saved you guys a little bit of trouble. We hadn't just talked about that, so I thought I'd introduce that here. So, any questions on that stuff so far?
So explicit prevents automatic conversion. I don't think this is a little different, but I don't think you had operator equals equals on the homework. I had to add that manually.
Maybe not. I think I may have. Yeah, I'm trying to remember if I snuck that thing in there or not.
I mean, it was helpful anyway. I don't know. I felt weird about modifying the h.h.
Yeah, that's okay. If you added that, that's okay. I think I have a vague recollection of trying to sneak it in there, and I might have missed it and put it in after some folks got started, or I may not have put it in yet into the starter. But thanks for pointing that out.
Yeah.
Okay, so I think we talked enough about these, so I'm not going to go into these super deep. But so last time we talked about copy constructor, which means we copy values from one instance to another at construction time. We of course talked about the destructor. We talked a little bit about the assignment operator, and we just introduced the word explicit there to kind of prevent the conversion, the automatic conversion from actually happening. So, and then there are all sorts of conversion operators we could add to a class. We won't look at that too much today, but that was kind of the collection of things we looked at on Thursday, the new stuff that we were kind of getting to know. So just to kind of have you get a visual on it, if you remember, the tilde symbol is how we start out a destructor, right? And we can just print a message, or we can actually delete stuff if deleting stuff is helpful, right? So there's our destructor. So we can do something like that. F equals new foo x, and then we can delete f, and that will actually result in calling the destructor. We never invoke tilde foo in code. If you find yourself writing down tilde foo on some line somewhere, then something's going to go very badly. So that's definitely not something that you would want to do. Also, of course, if an instance ever goes out of scope because of some braces, like inside of some function scope or local scope like that, then again, the destructor is going to get called. The copy constructor is a little tricky because it kind of looks like just another constructor. And as we've seen with method overloading and function overloading, that's really all that's going on here. The green constructor up top expects no arguments. So it's going to say hi. It's just going to be a default constructor. The blue one here actually is written, its function signature, if you will, is written to expect a reference to a foo instance, right? A const foo instance. And so that's its clue that, oh, hey, you're a copy constructor because I'm giving you an instance of foo. So what I want you to do is do the right thing to copy that instance of foo that I gave you on the right-hand side of the equals and set it equal to this, right? Either do a deep copy or a shallow copy or whatever it is that you should do based on that particular data structure. So even though there's no official way of naming a copy constructor a quote copy constructor, we know it's a copy constructor because we're basically sending in a copy of foo, right? And what we want back is a copy of foo. So it's like, oh, well, that's a copy constructor, right? So that's how that one kind of came to pass. Sorry, somebody in there. Okay, cool. All right, so so we can do that, right? We can create F1, and then we can say F2 equals F1, and that would be our copy process. It would not be like that. That's our assignment operator, which we'll look at on the next slide, I think. And of course, then we'd see by coming from our destructor. Okay, so that's our copy constructor. So let's see, just some highlights there. I won't go into all those, but sometimes I think, as we talked about, there's something called Elysian or EVO or RVO. It's an optimization where some compilers won't do the copy constructor. We're not going to really worry about too much of those. It's nice that that happens, but if you ever are surprised because it doesn't look like your copy constructor got called, it may be because the compiler you're using has some optimizations going on. Right. So here's our assignment overload. And remember, when we overload an operator, it's kind of like the name of the function that we're overloading is called operator, and then followed by the symbol. Usually they're together, right? Like operator greater than, operator less than. This is operator equal. That's our assignment operator. And all we're really doing here is, here copying the value from the right-hand side to the this value, right? And then we return an instance of that so we can chain stuff together. So that would be a very shallow value for value copy. But if this was that very complicated puzzle data structure we saw, we'd have to do a lot of code in here to actually make sure we duplicate all of that dynamic memory and then copy it over, right? So it's not just a little bit of work to actually write these things if you have a really complicated data structure. In this case, we're just copying the value over, which is what the default system level operator assignment will do for us anyway. So that's our assignment overload, right? Constructor, assignment overload. So we can do that, and then we can do F2 equals F1. So that, there's no construction going on here. All the construction happened at the F1 and F2 level. So that's why this F2 equals F1 is the assignment operator, okay? Now, if we don't want those default things to be in there at all, because we didn't rewrite them, we didn't do a good job of rewriting them, and we just don't want to allow any copy or assignment operations, then we can explicitly delete these things. So we can say foo const foo right-hand side equals delete. So that equals delete there tells the compiler, hey, I don't want your system level stuff in there. Please delete it so that any code that tries to do a copy assignment will stop the compile. It'll throw an error. Similarly, for the assignment operator, we can say equals delete, which means we don't want the compiler to do its default system level copy or assignment, right? So we can do that. And we'll see that the smart pointers in the standard container set actually, or in the standard smart pointer library that we'll look at, STD library will actually delete some of their system level constructors to avoid problems. So we'll talk a little bit about that. Right, so if we did F2 equals new foo F1, that would be an error because we can't copy. And similarly, that's a copy. And the third one there is an assignment, okay? So I think those are our big ones. Any questions on those, just kind of review-wise? We're going to be talking about these today, but in case you had any confusion on those so far. Okay, cool. All right. So these are just FYIs. I know you've seen this. I'm going to keep putting these Quizlet things out there. My hope is that they will help take some of the pain and maybe tear away on the final exam when we get closer. It's very much like the quizzes. They're just another way for you to practice and iterate on the core questions that I think will help you be a good coder as you kind of move on in your career. So I'll just keep putting those things out there. And remember that there's audio explanations in there. So if you don't understand why an answer is a certain way, you can click on the audio. I'm caught up. I think I have audio on all the ones that where it can be helpful, but I'll keep checking and trying to update that thing. And there are the individual links so far, and there'll be more coming. There'll probably be about 20 of them by the time we're done with the rest of the semester. Okay, and we won't do this now for the sake of time, but you can certainly click into that link and do learn mode on those things. Kind of introduce that before for you as well. Those are good ones. They're pretty easy. Once you do 3 or 4, you get the pattern, and it's just good exercise for your brain to recognize the code and what it means. So it's worth taking a look at that if you have a few spare moments. It'll take away a lot of the pain if you're finding some confusion there. Okay, so let's talk about Jigsaw Puzzle, which is our next assignment. I know some of you are still wrapping up on Boggle, so apologies for jumping into this so quickly, but we've got about 2 weeks on this, and like with Boggle, I'll keep coming back and trying to give you some tips as we go. But please read the Canvas instructions. I know it's a lot of words sometimes. At least skim it. If you think, you got it down from just the slides, okay, but, maybe go back and skim it, make sure you haven't missed something. I try to make that as clear as I can to help you out. But what I want to go through now is kind of a high level description of what we want to do with this exercise. And hopefully if you guys have any questions, you feel free to ask them now. But what we're going to do is, you can imagine this model where we have a box of puzzle pieces and they're in random order, right? And so for us, the text file is kind of the box of puzzle pieces. So we want to create a puzzle. The call our constructor is going to open the file, kind of open the box, read in all the descriptions of the puzzle pieces, right? From a file, it's going to look kind of like that. And we'll talk about what those numbers mean. And we want to create this dynamic array of pointers, right? Where each of those pointers points to an instance of a token. And the token for us is going to be a puzzle piece. And so what we're making here is just character puzzles, where every puzzle piece is just one character. I don't know if you've ever seen these things, but you can make some crazy pictures, of course, with lots of different characters. So that's what we're doing. Every token is going to be one character. Sometimes it's a blank, sometimes it's a backslash, it could be anything. And then it's going to have a location on a grid where that puzzle piece should go. So it's got a letter, which is really just the character, and then a row and a column, right? And they're in random order. So after you build this thing, after you build this dynamic array of dynamic size to all of these puzzle pieces, then you've got to go put them into a grid, right? And this is our good old friend, the vector of tokens, okay? So the trick here, though, is we're going to use pointers. We're not going to copy the token into the grid. We actually want to set the pointer of the grid to point to the appropriate token that goes at that location. And remember, we read these things in random order, so we really don't, it's not like we can just kind of read it in and then plug it into the grid. We got to read them all in, figure out how many rows and columns there are, because we don't know how many rows and columns there are, and then we got to put them in the grid, right? And so that's really what we're after here, and it will exercise all of these topics we've been talking about with dynamic memory, right? And then the last thing we want to do is print the grid, right? So there's printing of the list of puzzle pieces, and then there's printing of the grid. And the printing of the grid is the thing that actually draws the final picture, right? So you'll be able to get a picture, not this particular one, but you'll get a picture out of it that should be recognizable to you if you've got everything right. And that's kind of it. And then, of course, clear and delete the memory, right? So that you don't have any memory leaks. So that is a gradable part of the assignment. So if you forget to read about that in the Canvas and you don't do it, you'll lose a few points, not a ton of points, but it is an important part of the assignment. So please don't forget that part, right? So that's the high level concept. Our constructor is just going to build this part, right? And then we'll call a separate method to actually initialize the grid. So the grid initialization is not part of the constructor. The constructor is all about opening the file and reading in and creating the initial instances of all the puzzle pieces, which are just the tokens. Okay, any questions on that? So far, we'll definitely dig into this a little bit more. Hold on. Cool. There are ways to run, not with Replit, unfortunately, but very often in these type of classes, professors will use a program to check the memory kind of at start time and at ending time, and will report back leaks. So we don't really have that available to us, or actually we may be able to do it through some of the the launch commands for Replit. I've not checked it out, so but normally you would do it from outside of the program. Unfortunately, inside of the program, it's very hard to tell whether you've got memory leaks or not. But that's a good question, and definitely one that a lot of these auto grading programs with different universities will use to see if you have memory leaks. We won't get that particular about it, but I'll definitely be looking at your code to see if you do kind of the right stuff. So let's take a look at, let's dig down a little bit deeper just to make sure people kind of get a better understanding of how this stuff all fits together. So you're gonna have this file here. It's the puzzle text file, right? There's a basic text file, and then if you decide to do the bonus, which we'll come back to and talk about in the next lecture, but if you just do the basic one, you're gonna have a number of pieces. You're gonna have to read that many lines from the file, right? And each line is going to have a description of one puzzle piece. So the first number, it's an integer, it's an ASCII number, right, for a character, right? Because we're going to be loading in some crazy characters, and so we're going to need you to convert that integer into an ASCII character, which is a very straightforward cast. It is virtually automatic. So when you load it in, it'll be an integer, and when you assign it into a token, it'll convert to a character. So that's easy. And then we'll have the row number and the column number that piece goes in. And again, these are all in random order. So you're not going to really know what goes where until you read everything. And you're also not going to know what the largest row number is. You're not going to know ahead of time whether it's a rectangle or a square or it's taller than it is wider. The only way you're going to know is by watching all of these numbers as you read in and keeping track of what the largest row number is and what the largest column number is. And once you do that, then you'll be able to create your grid, right? So you have to read those in, track those numbers, and then you can come back and create your grid after that, right? And fill in the puzzle pieces, okay? And remember that your rows and columns start at 0. A lot of crashes last year because folks did not allocate 41, right? So if this is a 40, that's your largest number of columns, then that means you need 41 columns in your vector, right? In your vector of vectors. So please keep that in mind. So the token class has been fully written for you. So it's got row, column, letter. There's a CPP in there. Oops. There's a CPP in there for you. There's a .h in there for you. And I think I even have the OStream overload so you can print those things out if you want to. I'll go back and look, but it should be pretty straightforward for you to use that. And then puzzle.h looks kind of like this. So we have our constructor, right? And this is what I'll call step 1 for the assignment. You got to load in the puzzle pieces from the file, right? I'm going to pass you, or you're going to pass yourself the file name, right? And so your constructor needs to open that file. And then we'll have a method for printing the pieces, which is just printing that dynamic array of pieces, different than printing the grid. Separate from the constructor, we have this load grid. That basically says, okay, I want you now to go back into my pieces array and one by one fill them into the grid or load them into the grid. Those are what I'd call step 2 and 3 because we have to allocate the grid and then we need to copy the pointers into their correct locations in the grid. And then you can print the grid out and then you can destroy the grid, which will require that you destroy the dynamic array of pointers and all the individual tokens, right? So you'll need to do that to get full points for that. And then our private members are just the total number of pieces in the puzzle, the row count. This is the maximum number of rows and the maximum number of columns. And then our double pointer to a token, right? So this is an array of token pointers that we're going to be dynamically creating, or that you'll be dynamically creating in your puzzle constructor, okay? And then our grid, which is what gets initialized by this load grid routine here, okay? So we'll look at main to kind of give you a higher level picture how all this goes together. But any questions on that part there so far? Okay, cool.
You know, there's someone's got a bunch of questions in chat. Jack
Oh.
has a bunch of questions.
Oh, sorry. Thank you. Thank you for pointing that out. Oh, it was a little off to my side of my screen there. Did we, did I not answer all those? Oh, well, there we go. So. For two-dimensional grid, so it's going to be a vector of token. So you can, because, well, I think it's up to you to, if you want to do something that's not basically uniform, equal width of rows and columns. But I can tell you there's, there's going to be a puzzle piece for every possible location in the grid. So if it's, a 20 by 20 or a 20 by 40, you're ultimately going to need to actually initialize the pointers for every one of those rows inside of your vector of vectors. So I think that will probably be the most straightforward way to do that. And we'll look at that in a slide here or two. So just remember, though, that your constructor is going to build this thing, and then your load grid method is going to initialize the grid later, right? And we'll see how that lays itself out in main. So the key challenges here are that the pieces, again, are in random order, right? And you're really only allowed to read the file once. It'd be tempting to read the file more than once, but you're really just supposed to read it, load the pieces, and then come back and put them inside of the grid, right? And then again, you don't know the dimensions of the grid, so you'll have to pay attention to that when you're reading your data file to get the largest row and column number. And then you can initialize the vector of tokens, the grid basically, okay? So here's what that looks like in main, right? So it's pretty straightforward, really. We create our puzzle based on a text file name, right? So we're not passing in an open file pointer or anything. We're passing in the text file name, and our constructor has to open the file, read stuff out of it, close the file, all that, right? And then we can print the pieces, and after that, we can go ahead and load the grid, which is going to initialize the vector to the right size, and then put the pointers in it from the pieces pointer that's a member of the puzzle instance. Okay, so those two things I've separated intentionally to kind of make sure you get one before you move on to the next one. And then we can print the grid, which should print the picture for the puzzle. And delete of P. Now notice in main here, we haven't done this too much before, but instead of just saying puzzle P, we're saying puzzle star P equals new puzzle. So we're creating our puzzle instance on the heap, right? And we're returning a pointer to P. So here, when we delete P, we're saying is delete what P points to. In other words, delete the entire thing that's on the heap. And that should go to your destructor, and your destructor is going to have to walk through that dynamic array and delete the tokens, and then back up and delete the array and all that stuff. So we did a little bit of that last week. And we'll talk about it again. But that's really all your main looks like. And I think I've written that for you in main, so you don't even really need to write that part. I just wanted to make sure everybody understood how all these things kind of come together. And let's see, where are we after that one? So actually, yeah, before I move on then, kind of high level, I'm going to dig into the constructor and the print grid, and then we'll kind of leave this be for now and get kind of to the core of our lecture. Anybody questions on main or the puzzle class itself? Okay, all right. Let's see if we can kind of crank through this then. So here's kind of what we're doing with the constructor, right? So we're going to create our new puzzle here, assign it to P, which should create an instance of the puzzle on the heap, right? And we have those private members in the class. And this is just a pointer to a token pointer, right? So it's a pointer to a token. And we need that because it's going to be an array of pointers. And then we have our grid, which we're not going to initialize in our constructor. So our constructor is going to create that dynamic array, and then it's going to walk through and it's going to create all the tokens for it, right? It's going to point the pointers at those token instances. Okay, that's what our constructor is going to do for us, okay? So pieces of 2 is going to give me a pointer to a dynamically allocated instance of token, which should be the third puzzle piece that you read from the file. Okay, that's roughly how that goes. Okay. And then the step 2, we're going to need to allocate. Once we've done that, when we call our load grid, we know the maximum rows and columns at that point. So we can go ahead and create a row for row. And you can initialize those things with nulls if you want, and then come back and then overwrite that null with the right pointer. So you load in the right puzzle piece, right? So, or you can do it all in one go. It's entirely up to you. You can do it however you like. But essentially what you're going to do, given that you have this dynamic array of token pointers and the tokens, then you've got this grid with these null pointers in it. You're going to go find each one of those pieces from the pieces array and put them in their proper locations inside of the big grid, okay? So once you're all done, you'll have kind of copied the pointers over. So you will be referring to this token here twice. It'll be pointed to by a pointer from the dynamic array, but then it'll also be pointed to by its proper location in the grid, in the vector of tokens, okay, or vector of token star token pointers. Okay, questions on that? Okay, cool. Hopefully my picture will make sense when you look at it later, but we'll have the recording of this you can come back to as well. So here's some pseudocode really for you to really hopefully help you with this load grid. So the idea is for each row in the grid that we know we have to create, we can push back an empty row. And then for each column in that current empty row, we can push back, if you want, you can push back a null token pointer, right? And then later you can just come back and, at random, plug pointers in as you walk through the pieces array one by one. And remember, because those pieces are in random order, you may very well need to create all of your rows and columns up ahead. But if you can come up with a more clever way to do that and do these all in one step, that's totally fine, right? But as a thought exercise, you might want to think about this, right? So if we said grid of pieces of I row, grid of pieces of I col equals pieces of I, that's how we would actually assign that pointer. We're saying, hey, take the pointer at I and put it in its proper row column location in grid, right? So assuming you have initialized grid properly, so you've allocated all of the locations in the grid where you can store a pointer, and you've loaded all your dynamic array of pieces properly, you can make that pointer assignment just like that, right? So hopefully that might ring a bell when you come back to look at that particular code, right? That's just the row and column location of everything, okay? So that's kind of pseudocode for how you'll write your load grid function, okay? And then just syntactic reminders, if you come back to this page, I think I compiled this after grading last year, just kind of looking at the problems people had. Just kind of look at this code and remind yourself of, what these things mean, right? So here we're creating puzzle pointer to be a pointer to an instance. It's not the actual instance, it's just the pointer to the instance. And now we're assigning that pointer to a new instance of puzzle, and we're passing in whatever file we have that has the description of the puzzle pieces in it, right? So those are two different things that could be done all in the same line. That's totally fine. And here we're deleting puzzle pointer. We're just saying delete what puzzle pointer points to on the heap, right? That's what that does. And then here we can access a particular grid location, which will give us a pointer to a token, right? Our grid is not storing instances of tokens as we have in the past. For the first time, we're actually storing pointers in the grid. So when we get a grid like that, it's going to give us an instance that we can reach into and check the row or the column or the character or whatever. So here's something else we do. We say pieces 16, the 16th piece or the 17th piece we read from the puzzle, what's its letter? Because that's a pointer in that pieces array, I can access members of the instance that we're accessing through that pointer, okay? So I can get the token's letter that way, right? A row or column or any of that stuff. And if you've done everything correctly, the grid at this, I won't go through all this, but this should always be true, right? If you've initialized this thing correctly, you should always be able to kind of check to make sure these are the exact same instance. They should be the exact same instance, right? So that if everything went well, that should be just fine, okay? So that's just some hints on syntax. You may want to come back to that once you dig into the code if you're getting a little confused about what's what, because I know this is the first time we've there'll be pointers flying around all over the place. Hopefully everything's descriptive enough on the canvas there to help you get started. And there's your sort of jigsaw starter right there, okay? Any questions on that before we move on to the bulk of our lecture for today? Okay, I realize that's a lot. I just kind of wanted to get it out in front of you guys to get started. It's kind of a fun assignment. It's got a fun reveal. You know, it's a different puzzle picture than the one you saw, but it's hopefully enjoyable. So for today, we're going to talk about what we'll call smarter pointers. So while you're ruminating and working on this jigsaw puzzle with real pointers over the course of the next 2 weeks, we're going to begin our journey in talking about smart pointers or smarter pointers. So in terms of the standard library, smart pointers is a very elaborate set of classes that allow us to do very large scale development in a little safer way. But we're going to, before we jump into learning about that standard library, we're going to make our own baby version of those smarter pointers. That's what we're going to be doing today. We're going to do 4 exercises on how we would go about it, creating a smarter pointer, just like the way that the standard library does. So hopefully after we get through today, and we may stretch over a little bit to Thursday, you'll have a better set of context, understanding what this standard library is doing. And this is really the way you would go about building a system like this. So we're just going to tackle a few of the basic things. So we're going to follow this idiom we talked about, which is rule of threes, which means we need to actually have these copy constructor, what we should have the copy constructor or the assignment operator, or we need to delete them if we don't want them. And then we're also going to follow this idea called scope-bound resource management, right? Which is that if an instance goes out of scope, then all of the memory that instance allocated also goes out of scope. It's kind of like clean up your own mess. If you're an instance and you got created and you created a bunch of memory, then you need to clean up that memory when you get deleted or when you go out of scope, right? And we use the destructor to do that. So that is a huge, big pattern that a lot of people follow in designing these standard library things, because it means we don't have to worry about things like vectors leaking memory, right? When you create a vector from the standard library container and then it goes out of scope, it cleans itself up. It's really nice. It implements this idea of scope-bound resource management. So we'll be talking a little bit about that. And then we'll do our homemade version or class of pointers here. I'll call them smart PTR, just so they don't get confused with the true smart pointers we're going to look at on Thursday. And essentially, it's just a class that wraps around a raw pointer. And we'll start out looking at an integer, so you can kind of see how that works. And then we'll overload some operators so we can make it look in code like we're literally working with a pointer, even though we're really working with an instance of our smart pointer class. But to do that, we're going to have to, well, first we'll give it a random ID. We're going to overload its dereference operator. We're actually going to delete our system copy and our system assignment just to kind of keep things light. We don't have enough time to really write those in class today, so we'll just delete them. And then we'll overload the arrow operator, and we'll kind of convert our class to deal with tokens rather than numbers, just so we can see what it's like to actually have that arrow operator working. So that'll be what we'll call our smart PTR. That's our little mini version of a smart pointer. We'll look at that today with these 4 exercises, if we can get all that stuff still done in the time we have. And then hopefully that will set you up to understand the bigger topic of all of the standard library smart pointer stuff we're going to talk about coming up. Okay. So that's what we got out in front of us. So this is just one slide on this RAII, which is Resource Allocation is Initialization. It's a horrible acronym. No one can remember it, but you'll see it kind of referenced by kind of coding ninjas out there. It's also referred to as SBRM, or Scope Bound Resource Management. That basically just means what I said. If you create some memory, you got to clean it up, right? And the class itself is responsible for doing that, right? So that's kind of the best practice, right? So that's just in case that word pops up in the future, maybe you can remember what that is. I won't be testing you on that in any way. Okay, so let's dig into our smarter pointer implementation. So, so the first thing we got to do is make sure that these things clean up after themselves, right? So if I have an instance of a class that in some way refers to some memory on the heap, we kind of learned last time we talked about all this stuff, that when that FPTR goes out of scope for some reason, we want our destructor to automatically get called to clean up whatever instances that are pointed to. So we know we're going to have to do some writing in our destructor to clean up whatever our pointer points to, right? So if I have an integer pointer that's buried inside of this smart pointer instance, let's say, I'm going to have a constructor to clean up what it points to if I delete that particular thing, right? So we're going to use this concept to actually take care of that problem, right? So here's what we want to be able to do. We want to say smart pointer P0. So that's like creating a pointer. And in our case, we're going to start out by pointing to an integer, right? And then I want to be able to say, okay, PO equals a new integer, int 0, right? I want to basically assign P0 a pointer, right? But P0 is actually an instance of a class. So how is it possible that we can actually assign it a pointer to an integer? Well, we'd have to actually overload the assignment operator in order to allow us to take control of that. That's one thing we'd have to do. We could also overload the copy constructor so that when we passed it into the constructor for P1, we'd say, hey, I'm creating this P1 smart pointer, but I'm going to give it a pointer to a raw int on the heap. That would be another way we could get that thing up and running. And then the assignment operator would allow us to do, or sorry, that's another form of the copy constructor right there, sorry. And then that would be our dereference, right? So if we said, oh, I actually would like to get a copy of whatever you're pointing to, right? So P1, remember, P1 is actually just an instance of a class, but if we overload the star operator, we can actually make it behave as though it's, we're dereferencing a real pointer, right? So when we look at code, it looks like we're saying, oh, int x equals what's at the smart pointer P1. Well, smart pointer P1 is pointing to the integer 1. So it gives us what we want, even though we've gone through this process of creating a class that actually mimics what the pointer is doing, right? And the key bit there is we have to implement our overload for the star operator, right? And then we could do, we could write the assignment operator that way, so we can kind of control what goes on there. And then, of course, when it goes out of scope, we're going to have to delete all that stuff. Whatever it's pointing to needs to be deleted. So we'd have to actually deal with that via the constructor, or the destructor rather, okay? So that's kind of what we want. We won't get all that done today, but that's the goal, right, of creating a smart pointer, right? So here's our class to start. So we're just going to start off by working with integers, right? We could try to templatize this whole thing and get really fancy with it, but we're going to try to keep it simple. So we have a data member, which is a PTR, which is a pointer to an integer, right? And so when someone calls the constructor with an argument, they're going to pass us in a pointer to an integer, and we're just going to set the internal member PTR equal to that pointer, right? And then if somebody doesn't give us an argument, we're just going to set the pointer to null, because we just created a null smart pointer. And then, of course, when our destructor gets called, for whatever reason, we'll go ahead and delete what PTR points to. But we should probably check to make sure it's not null before we delete it, but that's what we'll do. So that's all we're really doing with our smart pointer. It's really pretty straightforward, right? We just have to deal with a few of these special operators, and potentially copy and assignment operators as well, but we're going to try to keep it simple. So so that's kind of the high level. Any questions on that? We'll dig into all of these different things that we're going to do to build this thing up today. Okay. I won't put anybody on the spot. I'm kind of hoping people aren't too lost. Feel free to give me a thumbs up if you're feeling okay about this. But
Could you templatize it? Sorry, could you
yeah,
templatize this?
absolutely. Yeah, good question. Absolutely, it'd be way, way, way better to templatize it, right? Yeah, but I thought, I was tempted to introduce that, but to be a bit much kind of in one lecture. But yeah, the nice thing to do would be to templatize that type right there, rather than int. Just make that a template parameter, and then it could be float, int. It could be a token, which we'll get to at the end of this particular set of projects. But yeah, that's exactly what you would do. Yep.
And then one more thing, I was going to say, you said our own version of a smart pointer class. Is there already a class with this?
Yeah. I mean, what we'll do is just switch over to using the standard library. There's what are called shared pointers. There's unique, shared, and weak pointers, which are all part of the what we call smart pointer class. I think it's in the memory library.
Huh.
So we'll get to know that pretty well over the course of the next 2-3 weeks. But this is kind of the two-step to getting there, because we wanted to build our small version of it first before we go deal with the, because once we go look at the library one, we'll forget how all this stuff works because it just works so well.
Yeah. Okay, cool.
Okay, thank you. Okay, so pointer creation. So we want to think like a pointer. So we want to do that, right? Which creates just an instance, right? It's a null instance. It's not pointing to anything. And remember, for the moment, our smart pointer is an integer-based smart pointer. We could also do that, right? So that would be passing in a pointer. Remember, new always gives us a pointer to something. So new int2 is passing in a pointer to this int2 that is on the heap. And our constructor is actually going to take that pointer and assign it to our private PTR member. So now our instance is holding on to that pointer to that thing on the stack by virtue of just passing it into the constructor. And when we use the standard library, it's going to work just like this. We're going to pass in pointers to things that are on the heap as raw data, and then from then on, we'll operate through the name of the instance sp2 or sp1, right? So there's what sp2 would look like, right? And then we could do another one like that, right? So that's our creation, right? So that's how we want it to go for creation. So let's look at what happens with deletion if we do our destructor correctly, right? So here's our class again. So smart pointer sp1, that's a null pointer. It's going to come into scope on the stack, right? And then it's going to go out of scope after that closing brace, right? So it comes into scope, right? It's a null pointer on the stack. And then it goes out of scope by virtue of the braces. And it's going to delete that thing. Well, the destructor is going to, if it had any memory, it would actually, the destructor would delete whatever memory we'd passed in. But since it's null, there's nothing on the heap. Now, in this case, if we do that, when we construct it, it does that. And then when our destructor gets called, because sp2 goes out of scope here, right? Then destructor's got a little bit of work to do, right? So now our destructor is going to go in and it's first going to delete what's on the heap, and then PTR, and then the sp2 will go out of scope, and then everything will be cleaned up nicely, okay? So that would be our destructor doing a little more heavy lifting. Same thing, just with a different invocation there, right? So all we really need to do that is just say if PTR not equal to null, then delete PTR, right? To be safe, right? So that's really all we would need to do to get that part of it working, which is pretty straightforward. So this is what we want to build. We're going to build it in 4 steps. The first one's super easy. It's really just getting used to the class. So what we'd like you to do is kind of what we did the other day. So apologies, it's a little bit of a rehash, but I'd like you to go into the class here. And you can kind of skip over this example, I think. And what we'd like you to do is go into the smart pointer class and add an ID to its members, right? And then inside of the constructor, we'd like you to actually set that ID to some random number. That way, when we print out some description of the pointer, we have a unique ID, or a pretty much statistically unique ID for that pointer. We can kind of debug things a little bit better. So that's going to be our first task, is to actually do that. So our class looks kind of like this, right? You'll see the code in a second. But basically, we have this private pointer we talked about. We're going to have you add the ID there. And in the constructor, go ahead and assign a random number to the ID. And then print out a description of that ID. It's like, hello, I've just created pointer with ID number such and such, right? And then assign the argument that we were given, P equal to PTR, right? And you can see here, because of my default setting, I've kind of collapsed my constructor into just one constructor. So I don't have to have the default constructor and the other constructor. It's just all one thing. So that's what we'd like you to do on this first one. And then when you delete, when the destructor gets called, print out a little message on which pointer ID you just deleted, and then go ahead and delete it, right? I think that code may be already there for you. So that's what we'd like you to do in your first one. So that is just kind of rehashing that. So go ahead and click into that link and let me know if you have any problems. I really shuffled some things around today, so hopefully I got all the links correct. But if you hit any bad links, let me know and I'll try to fix them. And I will kind of give you about 2-3 minutes on that one. Should be a pretty quick one. And again, the idea for the ID here is really just kind of a debugging thing. You may never actually implement that in any real code that you write, but it does help you kind of know what's going on when you're starting to learn this stuff. And maybe familiarize yourself with main too a little bit, because we'll be kind of creating pointers and deleting them and bringing them in out of scope just to exercise some of these different constructors and destructors. See if I can click in. I think if I click on this link, it's not going to change your screen any. You guys are still seeing the slide screen, right? Or the slide.
Yeah, I can still see the slide.
Okay, cool. Thank you. Thank you. Yeah. Okay. Stop that guy there. Okay. Right. So I'll just speak to this while people are wrapping up. But in main, the idea here, it's a little bit hard to, I realize, step into all that code that I wrote for you there. But basically, we're going to create a null pointer, right? And so if we say, you know, if we wanted to print it out, you know, we could just say C out sp1.ptr, right, which is a public member, right, and it would print the address of PTR because Replit will do that for us. And then separately, we could create an sp2 with an integer there, right, and print out the address to that if we wanted to. And then we create some local scope where we create sp3, which will, of course, go away after that second brace there. Sorry, I'm talking to a screen that you guys aren't seeing. I forgot that you guys didn't switch over. Well, we'll just do it the old-fashioned way. I'll just kind of look at the code here, I think, because everybody's probably there. So essentially, here's what we did with the ID. So we added our ID. We've kind of set our ID inside of our constructor. And then we'll kind of have a little printout just so when the destructor happens, we kind of know what went away. And I won't switch the view over to the code view, but you guys all could see main. Hopefully it makes sense with the comments there, what's going on. And let's see, I think probably, yeah, this stuff is kind of for later if you come back to that. But we'll see that there are some tricky problems with what we should do when we have a null pointer and we try to do something like a dereference. We'll look at how we manage that up in the next coming slides here. So let's add that. Let's do our dereference now. So the idea here is we want the overload so that if we create this and we say, what's that star pointer, right? And remember, PTR here in this particular slide is just the name of that instance. I probably should have called it something different so you don't get it confused with the member PTR of the smart pointer class. I should have just called it, you know, PTRA or something. But if we want to say, normally if we said star PTR, the compiler would complain to us and say, hey, wait a minute, PTR is not a pointer. It's actually an instance of a class. But since we're going to overload that operator, we can actually cause the class to give us what we want it to give us, right? Which in this case, we want to know what it's pointing to. So here we're actually creating the first kind of, appearance that this thing is acting more like a pointer if we can implement that particular overload, right? So that's what we're going to do in our next exercise, right? So here's how that would look, right? So if you recall, if we do an overload operator for star, right, it's really that simple. We want to return, when we dereference a pointer, a raw pointer to an int, we want to return an int, right? And we want it to be a reference in case we're using this in some chained operation. So the operator, the method name is operator star. Probably should have put a space in there for readability, but it won't make a difference. And all we're going to return to is what the raw pointer points to. Okay, so that overload for that method right there allows our class to do the kind of a first trick is acting like a pointer whenever we want to do a dereference. So we do that, and then we say cout star p, and that should print the number 5, right? We should even be able to say cout star sp plus sp, and that should give us 10, right? And then we should also be able to say star sp equals 10, right? So that would actually allow us to set 10 to what that pointer points to. And remember, it's all happening through the class, right? Because we overloaded that operator. Even though that's an instance of a class, it's sort of in code looking like a normal pointer would look like when we do that kind of operation, right? Very cool. Questions on that part? Okay, well, let's see if we can, I think I'm just kind of leading up to that, but so this is just an example of kind of the code, what the code might look like. I can say cout sp2, which will reach into via the raw pointer and get the 2 from there. So it's going through the sp2 class. The dereference here is actually, the overload is saying, oh, give me what the raw star ptr points to. So it's going to return that value right there, right? Similarly, for this, sp3 would return that value, etc. Okay, so that's what we're after. Okay, so let's try that. So you'll need to go back and look at that reference, I think, for that code. I can leave that up on the screen for you. Basically, this is going to be your operator overload there. So give that a try, see if you can implement that. And then I think the instructions are in the code, but essentially you want to do that and then go into main and try out some of that dereference and see if you can print out and convince yourself you're actually doing that properly. So I'll go ahead and set the timer on that and leave that slide up for you. I'll give you a couple more minutes on that one because that one's just a little bit more involved. Let me know if you have any questions. This will be the boring part of the recorded lecture when you guys play it back later. Unless I can figure out how to edit this stuff out. I guess I will get better at pausing the recording at these junctures in the future. Kind of go back to our layout here and see if there's any key points I can give you here. Yeah, so remember that this particular overload operator is returning what star points to. And because at the moment we're not using templates and our pointer is hardwired to point to an int, then that means that what we want to return from the function is actually an int. So it should match the type of the return value for the overloaded operator, right? Now that third bullet there does lead to that interesting question. So there is this small conundrum of what do you do when somebody tries to ask you to dereference a null pointer? What should you do? Well, we're supposed to return an integer, but we can't, right? If somebody gives us a null pointer, but the method requires that we return an integer, what do we do? Well, the right way to do that is deal with an exception. But we haven't got to that part yet. So we're going to kind of punt in this particular example, just print a warning and then continue on, which will probably result in a segmentation violation at some point. But that's a problem that we'll deal with at another time. But it's a good one, right? Because you figure there should be a good way to do that because it's going to happen, right? And it'd be nice if you didn't crash, right? It'd be nice if you could just be told, hey, that pointer is null, right? Don't do that kind of thing. So, and then this last bullet there, if you have time or you play with it, you might try removing the ampersand, the reference that is from the method itself. So you can kind of see in our overload here at the bottom, we have int ampersand operator star. If you take that out, that will prevent you from making an assignment to a star SP instance, right? So we need to have that in there so that we can chain these things together. But otherwise, that's all there really is to it. And this is that kind of punt thing I was talking about here. If the pointer is equal to null, then we're going to print a warning, but then we're going to try to dereference it anyway, which is probably going to crash, which is not the most elegant way to do things. Okay. So that's our solution right there. Okay. And then a couple observations for you if you come back to read this, but I think this is the stuff we've kind of touched on at this point. Okay. Any questions on the dereference part? Cool. All right. Well, this next one, let me see how we're doing on time. Yeah, I think we might be able to get through 2 of these guys. So this one is just sort of a little bit of cleanup. We really don't have time to implement the copy and assignment operators, which would be nice, but we're going to kind of punt, right, by deleting these so that at compile time, anybody that tries to do one of these things gets a warning from the compiler, because our particular implementation is not that smart. It's not as smart as it could be, right? So so the problem that we're trying to avoid is this one right here. Like imagine I create SP2, right? It's managing integer 2 on the heap. And then inside of some inner scope, I create SP3, which has its own integer on the heap. But then if I don't do something to delete the assignment operator, I could do something like this, SP3 equals SP2, which is going to just be a very shallow copy. It's just going to copy the pointer from SP2 into the value for SP3. So those 2 pointers, PTRs, point to the same pointer now, the same address on the heap. And now we have a leak. We've lost integer 3. It's sort of leaked into the heap, right? So that would be a bad thing, right? Because when this thing goes out of scope, it's going to delete its destructor for SP3. It's going to go ahead and clean up its memory. But guess what? SP2 here now no longer has its integer, right? So not only did we have 2 things sharing, but the destructor for SP3, when it went out of scope, deleted the integer that was now shared by both of these pointers. So it's doubly problematic to allow this kind of thing to happen. If you haven't done a good job of this assignment or copy constructor, then you can get into a lot of trouble when you have shared pointers, right? So that's the thing that we want to avoid. And so one way to avoid that, if we're not going to write those methods, is just to explicitly delete them so that the compiler will scream about it when it sees this line of code. And that's what we're going to do in our next assignment. We want to actually go ahead and delete those system level operators. So it's the same kind of thing with copy. I won't take you through the whole thing, but essentially we can run into the exact same problem if we're assigning something during construction of SP3. So then when SP3 goes out of scope, we just run into the exact same problem, okay? So we want to avoid that, right? So the best way to avoid that, if we're not going to take the time to write these two things, is to delete these things, right? So this is kind of the overall kind of summary of the problem. I think most everybody gets that. When we get to our standard library, we'll see there's a kind of pointer called a shared pointer, which actually keeps a reference count, which is pretty darn cool. So it knows how many things are pointing to a particular chunk of memory. So it does a really cool job of actually not deleting anything until the reference count gets down to 1. So that way we know that shared pointers can work together on different chunks of memory on the heap and not end up deleting stuff out from under one another. So that's something that the shared pointer instance will actually do for us. We're obviously not going to do that today, but I just wanted to point that out because that's the solution to that problem, right? The other solution is to delete these things, right? So we're going to actually do that, right? Which is going to prevent that one. And then we're going to do that, which is going to prevent that one, right? So by putting the words equal delete after the signature of the copy constructor or after the signature of the overload for equal assignment, we can prevent those things from happening if we don't want them to happen. And so that's going to be our task on the next project here. So go ahead, I'll go back, I'll roll back to the previous slide in a second, but what you should do on this one is click into that and then just add those 2 lines of code to your class and go ahead and compile. And it should cause a compiler error because in main that we were trying to do in this practice section, we were probably trying to do both a copy and an assignment. So once you see that compile error, you can go ahead and comment out the offending code in main and make sure that it runs. So I'll put this back up so you can kind of see reference to the code that you have to put inside of your class. So there's no body, right? So there's no body to the copy constructor. We just put the words or the text equal delete at the end of that. So, and let me know if you have any questions. I'll set a timer here so you guys can play around with that a little bit. Where did my timer go? There we go. Nope, that's not it. There it is. Okay. And I guess I didn't point this out, but the other kind of smart pointer we'll deal with from the standard library is called a unique pointer. And so unique pointer is very similar to what we're doing today. Unique pointer officially does not support either the copy constructor or the assignment operator because it is dealing, it's by definition only dealing with one pointer points to one chunk of memory. So no shared pointers, basically. Okay, maybe another half a minute here. Okay, let's take a look at the code for that. So pretty straightforward, really, very little code. Obviously, once you plug that thing in there, you've kind of taken away its potential to work in those situations. So that kind of protects us at compile time from doing things that might cause a crash if this particular class doesn't implement a good copy, like a deep copy, for example, right? So, and I think that's new from since C11. So it's, I'm not sure quite what folks did before then. So, um, so that's kind of cleaning that part up. And the last thing we're going to do is add an arrow operator. So, and we're going to do two things here. Since if you think about it, our class so far is a pointer to an integer, right? And so we really can't make use of a arrow operator for a pointer to an integer. There are no subfields or data members of an integer. It's just an integer, right? If it was an instance of a class, like the token class, we can use our arrow operator to get to the row or column or maybe letter of the token, right? So what we're going to do in this last exercise is convert our class to support token. And we'll have to make changes in 3 or 4 places to do that inside of our class. And then we're going to add an overload for the arrow operator, right? And so the arrow operator is pretty straightforward, right? So the name is operator followed by the symbol we're overloading. And then we want to return the actual address. That's really all we're doing here is we're returning the address so that it can be used to access a piece of code. So I think, let's see, if I have a pointer there where I say new token, and assuming I have a default constructor for token, that'll put a pointer for a token into my PTR member here, right? And then I should be able to say cout sp arrow letter, right? An arrow letter, that overloaded operator is going to return the address, right? So it's going to return the address right here, right? And then that address is going to actually be used to access the subfield letter, right? And hopefully that subfield exists at that address. But if we've done everything right, that should work just fine. And it acts like a pointer, right? It acts like it's getting an access via a pointer, through the class to the subfield of what's being pointed to by PTR over here, right? Which is pretty slick. So go ahead and try that. I'll roll back so you can kind of see that reference code again like before. But the first job is going to be to go through the constructor and all the methods and convert int to token, right? So, because we're converting our class. And here again, I mean, for those of you who want to try this, you could try to convert this into a template now. But to keep things simple, you can just convert int over to token if you want to do that. And then go ahead and add the overload for the arrow operator, as I'll roll back so you can see that on the previous page. And then try it out in main. See if you can actually create a token instance and then print out one of its public members, like the row or column or the letter, okay? And then we'll wrap up. That'll be our last one for the day, okay? So I'll go back to that code so you can kind of see how that operator gets put together. So I'll give you a few minutes on that one.
I think it's already solved inside the.
Oh, is
Yeah.
it? Okay.
But it's good to see.
Thank you. Thanks. Yeah, that was one I was sneaking in here at the end of the day to try to slide in there. I forgot to pull that thing out. Okay, well, good. Let's go talk about that. Thanks for letting me know. No point in sitting there in silence. So yeah, so we convert our pointer over to token type, but this could be a template, which would be pretty cool. Obviously, our constructor needs to be able to support the potential for passing in a pointer to a token now instead of an int, right? We've got that converted over. And then we've got our destructor doesn't really need to change because when we delete PTR, we're just deleting whatever it points to. And this is sort of a shallow delete. If this was pointing to some data structure that itself was very complicated, hopefully that data structure had a destructor and that would cascade and everything would happen, perfectly, right? So, but in this case, we just have a simple token, and probably it has no destructor on it, but it doesn't need it. And then here's our dereference overload, and there's our arrow overload, right? So they're really the same. It's just here we're returning what pointer points to, which would actually return the actual instance. And this is actually returning the address. Not to be confused with this that points to this whole instance of smart pointer. We're actually returning what the raw pointer points to, PTR, when we dereference here, right? And here we're just returning the pointer, the raw pointer itself that's stored inside of the instance, okay? So that's pretty much what the standard library is going to do, and it's going to do the assignment and copy operator for us as well in certain cases. But for the unique pointer, that we'll find the standard library will do this. For the shared pointers, the standard library has some pretty cool code to just keep track of references for us. In other words, every time we try to share a pointer, it's got a table where it keeps counters of who's pointing to what chunk of memory. So it's doing a lot of that stuff behind the scenes for us, and we'll play with that later in the week, right? So we can do something like this, right? So we can say new token A23, and then just print out as if it's a pointer, right? Even though we know that's not a pointer, that's an instance, right? All via overload, which is pretty cool. So next time, what we're going to do is we're going to look at this library, because we now have kind of walked around a little bit of how some of those things are implemented. And we'll talk about, what cases you would use these things. We will circle back, even though our homework that we introduced this week is using true pointers, raw pointers. We will come back to this homework assignment, and if we have time, convert it over to shared pointers. So when we talk about shared pointers on Thursday, we'll talk about what if we had done this homework assignment with shared pointers, even though you're going to be kind of moving forward using the old-fashioned pointers for this particular homework. We'll talk about how you would go about it, convert those over to shared pointers. And that'll actually end up being an exercise for us. It won't be too hard of an exercise. It's actually, it's a useful one. So that's what we'll do on Thursday. And otherwise, we are all wrapped up. And apologies for the folks last week that I bugged out for a couple minutes and then came back. And so I missed a few folks. So I will do better this time. I'll stay online for anybody who has questions for the duration. So that's it for today. Thank you. And let me know if you have any questions.